So the better way is the following. So I still have my delta j. So delta j, I'm going to still write it as the same partial j partial un times delta un. All right. I'm still have to linearize all my formulas. So the linearized formula is, if I write it in the general way, delta uk plus 1 minus partial gk partial uk times delta uk minus partial gk partial s delta s is going to be 0, right? So since the formula on the right hand side is 0, if I add this 0 to the objective function, it shouldn't matter, right? Well, but this 0 is not the same dimension as delta j, right? This 0, it has the dimension of uk, uk plus 1 actually, right? Because uk plus 1 may be a vector. So I need to make it a scalar by dot producting it with something. And that something, I call it uk, let me just call it uk hat. So uk hat has the, let me actually call it uk plus 1 hat. uk plus 1 hat has the same dimension as uk. So the transpose of uk plus 1 hat with this should be 0 because the formula inside the parentheses is equal to 0. So if I add it to delta j, which is this formula, I should still get delta j, right? And this is true for all the k's. So if I can add with k goes from 0 all the way to n minus 1, this is still delta j. The way to do this, this is a general technique, is assuming a certain constraint is satisfied, multiply the constraint, which is equal to 0, with something, and add it to the objective function. Is a technique called the method of Lagrange multipliers. This u hat is what's called the Lagrange multiplier in optimization terminology. So the adjoint method is basically also the same as the method of Lagrange multipliers, which is also backpropagation in this particular context. So once I'm doing this, the task is to get rid of all the delta. So first of all, the task is to get rid of delta un, right? This is what we did in the first step, to get rid of delta un so that delta j can be represented as a function of delta ui minus 1 and delta s. And then we also need to get rid of delta ui minus 1. And then we get rid of delta ui minus 2, etc., etc. So the task here is to get rid of all these delta u k's. So how do you do that? By choosing the appropriate Lagrange multipliers. Okay? So basically the task is, how do we choose this u hat of k's so that all these delta u k's is not in the formula? Basically we want to evaluate the effect of a parameter change, small parameter change, to the objective function without having to recompute all these changes in the intermediate states. Right? That's the goal. That's the goal of the adjoint. So to see how can we get rid of these delta u k's, we just collect all the terms. So this is delta un. So collect all the terms. First of all, the last term to collect is delta un, right? So for delta un, we have this and just this plus u hat of n transpose times delta un, right? So this is all appearance of delta un. And then for all the other uk's, delta u case, the appearance, they appear in two terms. They appear over here, and they appear also in as delta uk plus 1 in the previous k, right? So if you write down whatever is multiplied with delta uk, you have two terms. One term is this. That is, don't forget the negative sign. I have negative of u hat k plus 1 transpose times partial gk partial uk. So that's from here, right? So let me just denote 1. And we also have a contribution from here, right? The second term. But now we are focusing on whatever that is multiplied on delta uk. So the corresponding u hat should also be k. So I should also be u hat of k transpose minus this, right? And this is summed over all the way from k goes from 1. Is it 1? Yeah, it goes all the way from 1 to n minus 1. So the only term that was not included was the when the 1 term when k is equal to 0, which we assume is already 0, right? Okay, so we have taken care of this term, this term, this term. The only term left over is whatever that is not dependent on the intermediate delta un's. So the last term, after the elimination, this is going to be the only term standing. That is minus summation k goes from 0 to n minus 1 of u hat of k plus 1 times partial gk partial s times delta s. All right. So if we only want the red term to remain, we need to set everything in the parentheses to 0. Right? And how do we do that? We go backwards. First step, we set u hat of n to be equal to the transpose to the minus transpose of dj dun. Right? If we set un properly, this thing becomes 0. All right? And once we know what is u hat of n, that is appropriate to eliminate these delta un's, we go backwards. We see that, okay, I already know un. Now I know what un minus 1, which is the uk here, has to be in order to have delta un minus 1 to be eliminated. Right? That un minus 1, u hat of n minus 1 is equal to the partial gk partial gn minus 1 partial un minus 1 transpose times u hat of n. Right? So let me write the adjoint equations. So the adjoint equations for this is the first of all, I have u hat of n has to be equal to the transpose, actually minus transpose of this. So this is called the terminal condition of my adjoint, because this is like the initial condition for my adjoint, but it happens at the end of this forward propagation, right? And then I have u hat of k equal to partial g k partial u k transpose of uk plus 1 hat. So this has to be going from k n minus 1, n minus 2, etc. all the way to 1. All right? And once I go backwards through this whole calculation and compute all these u hats, then I know that the blue terms in the delta j is all zeroed. I only get the red term, in which I need these u hats, right? And the gradient of delta j to delta s is just everything here. Does it make sense? Any questions? This is exactly how you do backpropagation in deep learning. The formula just follows that. And when you have a discretized, explicit ODE or PDE, you also follow the same formula. Yes?
So what happens to the partial S term?
Yeah, the partial S term is going to stay non-zero. That is the term that gives you the derivative of objective function with respect to S, right? The objective function depends on S. So although in the definition of the objective function, it does not depend on S, but it depends on UN, and UN depends on S. So there is an implicit dependence of J to S, and that is what's given by this red term. Okay, yes?
So the red above UN, why is that the transpose? DJ DUN?
Oh, that's just a notation, because when I write DJ DUN, it's I'm thinking of Jacobian, right? If you look at the Jacobian, the number of rows is the length of the vector J. The number of columns is the length of vector UN. So if J is a single number and UN is a long vector, then DJ DUN is going to be a it's going to be a row vector, right? I need to transpose it to make it a column vector, which is UN hat. Yes?
I don't know how you went from saying that the term in the parentheses in the middle of the board is 0 to saying each component is 0. So I know that the sum of the UK, you had k plus 1 transpose times blah is 0.
Yes.
Right?
Yes.
But how did you make the leap and say that, you know, those individual components are 0? Couldn't they just, any combination of those components could be 0?
By components, you mean different Ks or different what?
So within the summation.
Within the summation, yes.
Yeah, you said that you had k minus you had k plus 1 transpose dgk duk is 0.
It's 0, yes.
How?
I want to make sure that all the delta UKs disappear,
Okay.
right? These different terms in the summation is multiplied with different delta UKs.
Yes.
It's a summation over k, right? So
Uh-huh.
not only, for example, not only I want delta UN to disappear, I also want delta UN minus 1 to disappear. So I want delta UN minus 2 to disappear. So if I want all these delta U k's to disappear, I need all these parentheses in all these k's to disappear.
I mean, but couldn't you also have them disappear with a different solution where those terms are non-zero and just sum up to 0?
So if these terms are non-zero but sums up to 0, they would only sum up to 0 for a particular set of delta UKs.
Yes.
Right.
That's true.
And in order to ensure that, I need to actually know what are these delta UKs.
Uh-huh.
And what delta UKs I have actually depend on what delta S I have. I want a general formula
Okay.
that is true for whatever delta S I end up evaluating, right? So the only solution is to have this is equal to 0 for whatever delta UKs that may end up appearing.
Okay.
That's
so
why
you could have multiple solutions to this equation, as a matter of fact.
I can have multiple delta S's, and
Yeah.
for all of these delta S's, the blue terms disappear.
Okay.
That's the goal.
Uh-huh.
The goal is for whatever delta S I have, I would get to the red formula, right?
Mhm.
So that makes it important for all the delta UKs to disappear no matter what their values are.